So I went through and looked at the problems that people were having trouble with. And sometimes when it happens, I look at it and I say, okay, it's just a formatting problem. Because a lot of times it'll tell me how many people have missed the first time. And a lot of times we'll get a problem that looks like this. You've done 1.45 times 10 to the 3, and WebAssign goes, no, that's not it, because it wants 1.45 e to the 3 for its format. That's WebAssign's format. And so I look at that and I kind of weed some of those out. But I also by now have the which ones people have missed and which ones people have asked me about, and have looked at a couple of them. So I'm going to set up a couple problems today to help you get through and get them in and be able to get them in your homework. But before I do that, I want to remind everybody that your first lab report, the lab report on the height of the building, is due on Friday. And you've got a place in Blackboard to put it in. Okay, you've got a place in Blackboard to put it in. So, we're going to start by looking at an example that if you get this example, you'll see it an awful lot. So let's start with the rock or the pebble or the ball or whatever being thrown off the building. So what's going to happen is we're going to throw a ball off the building. We're going to throw it straight back up, and it's going to just miss, and it's going to hit the ground. So that's essentially what we're looking at. So this is one-dimensional motion, okay? Because we're just going up and we're coming right back down. Now we're going to start with a velocity of, I'm going to go ahead and give it 9 meters per second. We're going to get a velocity of 9 meters per second. And we do have an acceleration in this case. If I'm in the x-axis, I may not necessarily have an acceleration. If I'm in the y-axis, I definitely do have an acceleration. And even though it doesn't necessarily give it to me in the problem, I'm always going to have acceleration due to gravity. And we're going to use the 9.81 meters per second squared. And Robert, can you start a piece of paper around for a sign-in sheet for me, please, sir? Thank you. So we always will have an acceleration due to gravity. It's also a vector quantity, and it's going to go down. So we have velocity is a vector quantity. It's going up, and we have this coming back down. So we can ask a lot of questions associated with this. We can ask what's the height from the top of the building. We can ask the height from the ground to the top of the building. We can ask the time that it takes to have the object hit the ground. We can ask a variety of different things. But there's some things about this that even though it's not stated in the problem, there's some things that we know. We know the velocity right there. What's the velocity right there?
0.
0. The velocity right there is 0 because we are instantaneously changing from an upward velocity to a downward velocity, so we know we have a 0 velocity there. From logic point of view, so don't even worry about calculating it out because we can calculate it out and solve it. But from a logic point of view, we also know the velocity right here on the way down. What is it?
0.
If it's 0 here, that's not 0.
Is it 9?
Yep, it's 9. The magnitude is 9 meters per second, but it's negative. Because remember, vectors have direction and magnitude. So it's actually a negative 9 meters per second. Okay? So we have our 3 equations that we use. We've got x is equal to vt, except in this case, this is when acceleration is equal to, is not, or this is when acceleration is equal to 0. When acceleration is not equal to 0, we have this one. And then we have v final is equal to v initial plus acceleration times time. And then we have v final squared is equal to v initial squared plus 1/2 at squared. So that's kind of our toolkit. So let's say we want to know, and usually at this point we have to know something else. We either have to know the height of the building or we have to know the time that it takes to hit the ground. Okay, so I'm going to give us the time that it takes to go from when it passes me here to when it hits the ground. I'm going to say that it takes 3.5 seconds to hit the ground, and we're making an assumption that it doesn't hit terminal velocity due to drag. That we're going to be in that short part of a range, that it's not going to have a terminal velocity due to drag. So I'm going to give you that piece of information there. So you guys have a homework problem, right? The homework problem is I drop a ball, and it's going to fall, and then we've got the sound of the fall comes back up, and the time for this thing right there, the time for this whole thing is given to you as, I'm going to use 4 seconds, everybody has a different time. So the time that this takes is the fall plus the return of the sound. And I even think the problem gives you what the speed of sound is that they want you to use. So they give me the speed of sound as 343 meters per second. Okay, 343 meters per second. So if from the time I drop the ball to the time that it falls back or comes back up and the sound comes back up, I'm going to have a distance that I have to calculate. That's velocity times time, and this is the distance that the sound travels. 343 times whatever my time is that it gives me in the problem, and that is, did I do a bad thing and not bring my calculator? Probably did a bad thing and not brought my calculator. Nope, I brought my calculator. So 343 times my 4 seconds, that happens to be 137.2 meters. That's the distance that the sound traveled. That's the distance that I know, and the sound travels once it hits the water, right? So this is the distance calculated by determining how far the sound traveled. You calculated a distance by doing you calculated this by knowing that I dropped the ball and I'm using gravity times my time. You're going to compare the two distances by using a percent error. And percent error is real minus measured divided by real times 100%.
I have a question.
Uh-huh.
How'd you get to 137.2 from 343 times the seconds, which was 4?
I did 330, oh, sorry. It's not 0.2, it's 72. I had a dot on my calculator screen.
Okay.
Sorry. Because when I'm looking at it now, the dot's in a different place, so we're good. You're right, there shouldn't have been a 0.2. But it's 372 meters is what the sound traveled. Now, I don't know if your problem actually gave you a speed of sound, or you want to use 331, it assumes a cold, dry day, but that's basically, you've calculated distance using this value, and you've calculated distance using that equation. And you're comparing the two. So the trick to this problem, remember a lot of these things are tricks, the trick to this problem is realizing that this time that you're here is not the whole time that the ball, it has nothing to do with the time that the ball was in the air. But my stopwatch takes into account the fall and comes up. So you have some comparison. Actually, this isn't correct either, because this time takes into account the fall of the ball plus coming up with the stopwatch. So this is actually twice the distance that's called for. So you have to divide that by 2.
Can you lift the paper?
Oh, sure. Yeah, this actually takes into account the entire fall and coming back up, so that's actually twice the distance. Because it's got to go, so it's like doing a ping with a fish finder.
But that's assuming the ball is immediately falling at 343 and keeps that all the way down.
No. That's the sound. Because the sound's only going to travel this part, right?
But isn't the ball going to be a lot slower going down? So wouldn't that?
This doesn't have anything to do with speed. This only has speed of sound. We start the stopwatch here. Hit the stopwatch. Ball's going to fall. It hits the splash. Sound travels back up. The distance that the distance that is in that time period accounts for the fall of the ball plus the sound coming back up.
And so, I mean, if 4 seconds, so that would mean it would get up to like 37 meters per second tops. That's how fast.
Right, that's how fast the ball falls.
So-
But we don't have to worry about how fast the ball falls because we're worried about the distance that the sound is traveling.
What problem is this?
Number.
I think it's number 14.
Yeah.
Because when I could have swore they were asking for the distance the ball falls,
Well, part A is at the distance the ball falls.
and then
Part B is the percent error.
Yeah,
But I
so don't we have to
thought
find the
using the
distance the ball
percent
falls?
error, you would just
No,
not
you just
use
have to
speed of
find
sound,
the-
and you just
You
use.
just have to find the time sound moves since we already know the velocity of sound per second.
Yeah, the speed of sound is known.
But on the percent error, it says resulting from assuming the speed of sound is infinite. So wouldn't we just disregard speed of sound and we would just calculate the velocity, the time it took for the ball to fall?
You could do it that way too. Yeah, if they say the speed of sound is infinite, then you want to calculate the time it takes to have the ball fall 64
And then that's
64
all-
meters or whatever the
that's
actual
all-
value is.
and then
Yeah, you can do it that way.
That's how I do it.
Well, and that's actually, the way they're asking the question, that's actually correct. But from a logic point of view in the sound, this is what you gotta look at. I have it in 2 different books with 2 different solutions, so.
Yeah, this one's asking for the depth of the chasm.
Yeah, well, so you figure the depth of the chasm based on the time that you calculate, right?
Yeah, so which would be the time it takes for the ball to fall plus the time it takes for the sound to come back up.
Exactly.
That all comes out to be, for me, it was 3.3.
3.3, yeah. So that's the thing. So when you're looking at these problems, you've got to look at, that's always one of the caveats. You always have to look at the question that's being asked. Because a lot of times when you're sitting there thinking through the logic of the problem, the question that's being asked isn't necessarily one you're working at the time. And that's what happens with this particular one. You know, if I deal with my ball that's throwing off the top coming back down. Yeah, we end up doing this problem several times over the course of the 2 classes because we're going to do it with the echo coming off a wall. When we measure speed of sound, we're going to do an echo. So we end up doing this piece several different times, but we're going to ask a slightly different question every time. So not knowing exactly how the question was asked, then you say if we assume the speed of sound is infinite, we calculate the time. You can calculate the time that it takes to fall 64 meters or the time that it takes to fall however many meters you calculate it. And you know that there's a difference between the 2. And you can do the percent error with the time. Sam, did you do the percent error with time or did you do percent error with distance?
I think I did time.
Yeah.
Mine works at.
Yeah, if you compare time, that's one thing that you would do.
Oh wait, I did that.
You did that. So there's a couple of ways to approach it. But that's one of the things that's out there. Okay? So we've got those pieces that are there. This one, so we can do a lot, like I said, we can do a lot of different things here. We can calculate the time that it takes to reach the maximum height. Well, that's easy enough. V final is equal to V initial plus AT. V final we know is 0. We know the initial is 9 meters per second. We know that we have a negative 9.81 meters per second squared times time, because that's my acceleration due to gravity, that's my time, so I get 9 divided by 9.81 is going to give me my time. So if I do that, because I'm using those numbers. This gives me 0.917 seconds. So if I'm asked for the total time it takes the ball from the time it leaves my hand to the time it hits the ground, we now have time up here is 0.917 seconds. By symmetry, we know that this is 0.1 or 9.1 seconds, and we're told that time. So time total is going to be 2 times my 0.917 seconds plus my 3.5 seconds. So the total time the ball is in the air is 5.33 seconds. That's the total time the ball is in the air. We can also find the height from here to there. If I find the height from there to there, I'm going to do that h, height, is going to be my initial velocity, 9. We found that it was 0.917 seconds minus 1/2, 9.81, 0.917 squared. That gives me 4.13 meters. So now we can also calculate the height here. This case, I'm going to do that height is minus 9 times my time. .5 seconds minus 1/2, 9.81, 3.5 seconds squared. That fell a negative 87.5 meters, but that's the distance from here to here. So if we want to know the distance from here to there, we've got the total distance is going to be 4.13 plus 87.5. Oops, went the wrong way. That gives me 87.3. And that's the magnitude. This negative says it's from below this spot if that spot's 0. So we can ask lots of different questions, lots of different things. I can also calculate, oops, yes, let me get away with it. That's not that right there. That's 2a change in h, or change in height, or change in x. Sorry, I wrote down the wrong equation. And that's 2ax. You could solve it directly using this one, because that makes it easy. And I don't even need to know time for that one. I could find the total height that it falls right here. If I know the final velocity, so I can find a variety of things and I don't have to use the same one. $87.3? That was, well, I didn't. I added it wrong again. That should have been 91.6. Yeah, because that's 87.5. I added 4.13. Obviously, I'm punching something in the calculator wrong. Okay, so I'm going to use the lovely rocket car one. So let's look at the rocket car problem. So this is my version of the rocket car problem. I'm going to scroll in. Now, the idea behind the rocket car problem is, number one, they give you lots of extraneous information. This whole problem is lots of extraneous information. Things that we're told. We're told that ignited however many miles from the crash site, and then it quickly reaches the speed. We're told that the time that the rocket is firing is 25 seconds. Okay? Or the time that we've got is 25 seconds, and we've got 254 miles per hour. So that is velocity and time data. So part B is doing 254 miles per hour for 25 seconds. So that's just going to be D is equal to VT. You got to change your units and get your units straight, but that's that one. The other one says we went 4.8 miles from the crash site, and then the car remained on the highway for 3.6 miles. My change in position is 4.8 minus 3.6. That's position data. And we're told that its change in time is 25 seconds. Well, that's my position data. That's just my position data because that's all I had. And then we have velocity versus time data. So all that other stuff in that problem is just background. It's just totally background. It has nothing to do with the calculations that you have to have. So let's do one of my favorite type problems. So not only is the roof of the building problem my favorite part. So we all know that my RT stability is limited. So I've got my lovely little car here, and I'm going to be at the stop sign. And I'm going to have an initial velocity of 0. We're going to take, 15 seconds to reach a velocity of, we'll do 20 meters per second. We're then going to travel 40 minutes at a constant velocity. And after 40 minutes, we're going to apply the brakes. and we're gonna travel a distance of 200 meters, and we're gonna come to a stop. And that's 200 meters. I wanna know the total time, and I wanna know the total distance. I wanna know total time, and I wanna know total distance. So to do this problem, I gotta break it up into 3 parts. So we'll break it up into 3 parts. I'm gonna look at this part, and I'm gonna look at this part. So there's my 1, 2, 3 parts. Now for this one, I've got, for the part 1, time 1 is definitely 15 seconds. And I know time 2, that happened to be 40 minutes. So I've got to convert that to seconds, because we're going to work in seconds. That's 2,400 seconds. I don't know time 3. I don't have anything for time 3. I don't have anything for time 3. So then I've got distance 1, I don't know. Distance 2, I don't know, but I do have distance 3, that was 200 meters. So to find total distance and total time, I gotta figure out a few things. So let's do 3 first, let's solve for this one first. So in that case, if I'm looking at part 3, I have an initial velocity of 20 meters per second. I have a distance of 200 meters. And I have a final velocity of 0. I don't know an acceleration, and I don't know time. So I have a couple of equations. I've got the position is equal to v naught times time plus 1/2 at squared. That one's not going to help me out at all. Not so much. I've got v final squared is equal to v initial squared plus 2a change in position. Ooh, that's going to help me out. That's going to help me solve for a. And then once I have a, then I can solve for time, because that's v final is equal to v initial plus at. So let's do that. So v final squared minus v initial squared divided by 2 times my change in position is going to equal my acceleration. So in this case, my final velocity is 0, so this becomes minus 200, or sorry,
20.
minus 20 squared divided by 2 times 200. And this is going to be in meters per second, squared squared. This is meters per, that's just meters. That's going to give me an answer in meters per second squared. So I get 20 squared divided by 400. Oh, that's nice. That equals minus 1. And that's in meters per second squared. Now this minus indicates a deceleration. That minus gives me a deceleration. So now I can plug that into this one. And I'm going to solve for time. V final minus V initial divided by acceleration is going to give me time. Final 0, my initial velocity was 20 meters per second. I'm dividing it by a minus 1 meters per second squared. Meters cancels, 1 of the seconds cancels, and I end up that takes me 20 seconds, if I've done my arithmetic correctly. So now I can put that back up here, that's 20 seconds. So the total time is gonna be 15 seconds plus 2,400 seconds plus 20 seconds gives me 24.35 seconds. So now let's calculate total distance. So the first part, I have an initial velocity of 0. I have a final velocity of 20 meters per second. I have time is 15 seconds. I want to find distance, so distance is equal to v naught t plus 1/2 at squared. That's 0. I'm going to need acceleration, so I'm going to have to calculate acceleration again. I'm going to have to calculate acceleration again. Well, this time I have time, so I can do v final is equal to v initial plus acceleration times time. V final minus v initial divided by time is equal to acceleration. So this is 20 meters per second minus 0 divided by, we said 15 seconds. That's going to give me 1.33 meters per second squared. Plug that back up into distance. My distance equals 1/2 1.33 meters per second squared times my time, which was 15 seconds squared. That gives me a distance of 150 meters. So I put that in my little handy dandy table. Now the next one is we travel 40 minutes at 20 meters per second. Distance is just velocity times time, so we can do that. So that's 20 meters per second. And we said that was 2,400 seconds. Gave me 48,000 meters. So I can plug that in there. So my total time was 24.35 seconds. I've got 48,200. So my total distance is 48,350 meters. And now I can calculate an average velocity. My average velocity is just going to be my change in distance over my change in time, and that's going to give me my 48,350 divided by 24.35 is going to end up giving me 19.9 meters per second for the entire trip. That's the average velocity for the entire trip. But we had to take each section individually to calculate what we needed in order to give me the ultimate average. So this is starting to make a little more sense. We got sort of nods. How about you guys over there? I got shaking in the head. What's your problem over there?
That was a lot of work.
Huh?
That was a little bit like all over the place, it seemed like for me.
And actually, that's one of the problems with these problems. There's more than one way to do it. There's more than one way to do it. I got a couple of different equations to be able to do it. And that's why when you're working physics problems, practice, practice, practice. Okay, so let's do one because this is calculus-based physics. And even though you guys haven't had it in the calculus, we're going to work through it again just so that everybody can see it. So when we're doing average velocity, so we're doing our average velocity, that's our change in position versus a change in time. If we're doing speed, speed is related to the total distance divided by the total time. So speed and velocity, while they're related, and we use the terms interchangeably, they're not the same. So you guys have a problem that's got Michael Phelps going through the pool here. Here's the length of the pool. Part of the problem is he's going to go the length of the pool, and then he's going to come back. Okay, he's going to go the length of the pool, and then he's going to come back partial way, and then he's going to go the length of the pool, and he's going to come all the way back. This is T1, and this is T2. Average speed, so my average speed is going to be the total, it's going to be 2 times the length of the pool, T1 plus T2. Average velocity, 0. Because where we start and where we finish are exactly the same place.
Displacement over time.
Displacement over time. Okay? Average speed, totally different. Average velocity, a little bit different there. Now, we also talk about instantaneous. Instantaneous, if I can spell right, okay? Now, for calculus-based physics, we can take that derivative with respect to time, and that's going to give me my instantaneous. And so if I have a function, so I'm going to do, this is AT squared plus BT plus C. And I'm going to take the derivative with respect to time. I'm going to get A times 2T plus B. And there's no time here, so this goes away. The general function is, if this is derivative of x with respect to time, because this is what x equals, this is going to be a n t n minus 1. So if I have t to the third, I have 24 t to the third, that's going to be 24 3t squared. And so you do have a couple of problems that have you, let's calculate the instantaneous one. And so you calculate x at a time value t, plug it in the number, and then you're going to do, here's my x1, and then I'm going to subtract, or here's my x2, here's my x1, and here's my change in time. And how I'm going to figure that out is I'm going to plug in my time 1 in there, and I'm going to plug in my time 2, then I'm going to figure it out there. But when I want my instantaneous one, dx dt is equal to velocity, and I want my instantaneous velocity, then I'm just punching in my time value in that spot. Now, our textbook does a pretty good job of explaining it because you'll probably get it about midterm in the semester in calc. But when we're talking velocity, this is really the quickest way to get us to our answer, especially on instantaneous. But that's what the math is trying to tell us. Math is trying to tell us that, and that's what we're also trying to figure out on a graph. So, you also have a problem, and I'm not sure why this problem was causing people consternation. So this was the problem. You have a light can be described as a wave, and it gives us the speed. And then we get Sirius as the brightest star in the night sky is as 800 or 8.18 times 10 to the 16 meters from Earth. Find the time that it takes a photon to get here. Well, I'm not going to do Sirius. I'm going to do Betelgeuse. There's a reason I want to do Betelgeuse, and I've actually put it into your blackboard. Betelgeuse is doing some weird stuff right now. Betelgeuse is in the constellation Orion. And we want to know how far away Betelgeuse is. So somebody goes and looks it up, and we find out that Betelgeuse is 642.5 light years. And we know that the speed of light is equal to 3 times 10 to the 8 meters per second. So 1 light year is the time that it takes for light to travel in a year. So we want to know how many meters that is, okay? So 1 year, we got to put it in seconds, is 365 days. And there's 24 hours in a day. And there are 3,600 seconds in an hour. So if I plug that in the calculator, 1 light year is 365 times 24 times 3,600 gives me 331,536,000 seconds. Okay? Well, that's 642 of those, so we'll multiply 642.5, gives me 2.026 times 10 to the 10 seconds is how long that photon, if it left Betelgeuse, and we're seeing it today, it's going to take 2.062 times 10 to the 10th seconds for that photon to reach us. So if that's the case, my speed, which is equal to 3 times 10 to the 8 meters per second, is equal to distance divided by time. So if I take speed times time, that equals distance. So I'm going to take my 3 times 10 to the 8th, and I'm going to do 2.026 times 10 to the 10th seconds, and that's meters per second. I'm going to multiply that times, times 3 e to the 8, gives me 6.07 times 10 to the 18 meters. I'm going to divide that by 1,000. That gives me 6.08, because it's 7, 6.08 times 10 to the 15 kilometers. And it's a kilometer is 0.62 miles. So I'm going to multiply that by 0.62. That's 3.77 times 10 to the 15 miles. So that's, so it's a matter of just looking at the information that we're trying to deal with. So to give you guys a feel for something, I'll let you question here in just a second. That line right there, roughly the diagonal of an 8.5 by 11 sheet of paper, is the time that it takes for an electron to travel in one, or that's the distance an electron will travel in 1 nanosecond, 10 to the minus 9. That's roughly the distance of a nanosecond. That gives you the distance of a nanosecond. So when you're talking 642 years, that's a long way away. And actually Betelgeuse is one of our closest neighbors in terms of stars. And Betelgeuse is acting funny. Right now Betelgeuse was the 10th largest or the 10th brightest star in the night sky. Now it's like the 20th. It's going through a dimming phase. It's in the constellation Orion. All right, Brenda, you had a question?
I was just gonna ask, when you put miles, do you just put the M? 'Cause
Oh, I usually put MI. I just didn't do it on this piece of paper. I just usually put MI. You guys over there, how you guys doing over there in Enid?
When's our exam on this?
Do what?
When is our exam on this?
The exam I'm looking at, I want to get through vectors, and I wanted to kind of start vectors today. I'm guessing the exam in here is going to be next week. Be next Friday. So it's going to be Friday, February 7th. And it'll cover chapters 1 through 3, which will include vectors. Before we get to two-dimensional stuff. Because I'll do vectors on Friday. Other questions over there? So Friday, I'll see most of you in the lab Friday morning after my 10:30 class. Because we got to get the picket fence lab done. Labs are due for both sides on Friday. And that's the lab on the height of the building. Lab on height of the building.
is there a specific time it needs to be signed?
5 o'clock. Yes. Lab's by 5 o'clock on Friday. And and I will have for you guys, if you want to do gravity on an inclined plane on Friday, I'll have at least that part set up as well over there so you can get a week ahead if you want. Although that one does take a while to do, so it's usually one you want to do by yourself, although we had several people yesterday do both of those. There are a couple of labs that's really easy to do 2 labs in a time period. Okay, I got the,
I gotta go ask a question. I got a question.
any other questions, everything else good?